Welcome, dear learners. Greetings for the day. Today, we are going to learn Corrosion of Metals Part 2. In this part, specifically, we are going to learn about factors affecting corrosion. In my previous video lecture, we have covered Corrosion of Metals Part 1. In that, I have covered the basics of corrosion, the cause of corrosion, then what is electrochemical series, what is galvanic series, what is a dry corrosion, what is wet corrosion, and then we have seen an example of galvanic cell. Now in this lecture, we'll be learning about the factors affecting corrosion. Now, corrosion is a kind of reaction that takes place in the metal by the influence of its environment. Means when metals are exposed to environment, different environmental condition, it undergoes corrosion. Hence, the rate of corrosion depends on the nature of the metal and the nature of the environment. Both plays a very important role in determining the rate of corrosion. Now, the nature of the metal is divided into some categories, some points. They are position of metal in galvanic series, nature of oxide film, then relative area of anode and cathode, purity of metal, physical state of metal, then solubility of corrosion product and volatility of corrosion product. These are all very important points from the point of view of nature of metal, how it affects the rate of corrosion. So we'll discuss one by one. The first one is position of metal in galvanic series. In my previous lecture, I have explained you what is galvanic series. When the electrode potential of all the metal ions and even alloys is calculated in a common environment, which is a seawater, and then we arrange the metals in order of their electrode potential, we get a series called as galvanic series. Now, in this, there are some examples of metals are expressed from galvanic series. This galvanic series has two ends. One end is anodic end and another end is a cathodic end. Anodic end, towards anodic end, the electronegative metals are present. So there are more active metals on this side, and this cathodic end is an electropositive end and less active metals are present on this side. So how the rate of corrosion depends on the position of metal in galvanic series. The metals which lies towards the anodic end are more reactive and they are more prone to corrosion. And metals which lies towards cathodic end, they are less active metals and they are less prone to corrosion. So the metals higher in series is more active and suffers corrosion. The rate and extent of corrosion is directly proportional to the electrode potential difference between them. So if we connect any two metals, like here the example is taken, zinc and steel. So steel lies towards the cathodic end and zinc lies towards the anodic end. So if we connect these two metals, then zinc will act as an anode, and by undergoing corrosion, this zinc will protect the steel. So the position of metal in galvanic series is a very important point in determining the factor affecting corrosion. The second is nature of oxide film. Now, we know that when metals are exposed to environment, a layer of oxide film is deposited on its surface. Now, whether the corrosion will further continue or not, it depends upon the nature of the oxide film. So when metals are exposed to atmosphere, practically all metals get covered with a thin surface film of metal oxide. The ratio of the volume of metal oxide to the metal is known as Peeling-Bedworth rule. Metals can be classed into two categories, those that form protective oxide and those that cannot. The protectiveness of the oxide is ascribed to the volume of oxide takes in comparison to the volume of metal used to produce this oxide in corrosion process. The oxide layer would be unprotective if the ratio is less than unity because the film that forms on the metal surface is porous and cracked. Conversely, the metals with the ratio higher than 1 tend to be protective because they form an effective barrier that prevents further oxidation of metal. So, the nature of oxide film is very important. If the oxide film is such that it acts as a barrier between the metal and the environment, then corrosion can be further minimized. And if the nature of the oxide film is porous, then the corrosion may further continue. So let us see the next slide. For good oxidation resistance, the oxide should be adherent to the surface. The oxide should adhere tightly to the surface of the metal. The peeling bedworth rule, how we calculate it? The volume of the oxide formed divided by the volume of the metal consumed in the oxidation. Now, this peeling, we will discuss here the different values of peeling bedworth ratio. If peeling bedworth ratio is less than 1, then the oxide coating layer is too thin. Hence, it's likely to broken and provides no protective effect, and the oxide layer cracks. The example is magnesium. If the peeling bedworth ratio lies between 1 and 2, the oxide coating is passivating and provides a protecting effect against further surface oxidation, and it uniformly covers metal surface and is protective in nature. For example, aluminium, titanium and nickel. If the peeling bedworth ratio is more than 2, then because of too much compressive stresses in oxide film, the oxide coating chips off and provides no protective effect. The example is iron. Here one table is given where you can see the peeling bedworth ratio of different metal ions. Like you see, for potassium it is 0.474, for sodium 0.41, magnesium 0.81. So these alkaline earth metals, they have a peeling bedworth ratio less than 1, so they forms a non-protective layer. Here you can see aluminium, lead, nickel and titanium. The value is between 1 to 2, so they form a protective layer, and iron has 2.14, so the chips they fall off and they will not protect the metal from further undergoing corrosion. So nature of oxide film is a very, very important point. The next point is relative areas of anode and cathode. The rate of corrosion is greatly influenced by the relative sizes of cathodic and anodic areas. Smaller the anodic area and larger the cathodic area exposed to corrosive environment, more intense and faster is the corrosion occurring at anodic area, because at anode, oxidation takes place and electrons are liberated. At the cathode, these electrons are consumed. When anode is smaller and cathode region is larger, all the liberated electrons at anode are rapidly consumed at cathode. This process makes the anodic reaction to take place at its maximum rate, thus increasing the corrosion rate. If the cathode is smaller and anode is larger, reverse process takes place, which decreases the rate of corrosion. Now let us discuss this point with the help of this example. There are two examples, A and B. The first example A, here there are steel plates, they are connected together by aluminium rivet, and the second, they are aluminium plates, they are connected by a steel rivet. Now if you look at the galvanic series, what you see, let us see here. Where does the zinc lies? The zinc lies towards the anodic end and steel lies towards the cathodic end. So here these two metals are in contact. So zinc will act as an anode and steel will act as a cathode. Now see here. Here in both the cases, this aluminium will act as an anode and steel will act as a cathode. In the first case, the area of anode is very small as compared to the area of cathode. So as aluminium is an anode, it will undergo oxidation and it will liberate the electrons. These electrons are accepted by the steel plate. As the area of cathode is very large, the electrons are rapidly consumed at the cathode. Hence, the electrons are provided by the aluminium undergoing rapid corrosion. Hence, here the area of anode is very small as compared to the area of cathode. The intense and severe corrosion takes place. On the other hand, in the second case, there are aluminium plates connected by steel rivets. In this case also, aluminium will act as an anode and stainless steel will act as a cathode. But here the area of anode is very large as compared to the small area of the cathode. Hence the requirement of the electrons is very less by the stainless steel. Hence the extent of corrosion will be less. Hence the areas, relative areas of anode and cathode plays a very, very important role in corrosion rate. The next is purity of metal. A pure metal is more corrosion resistant than an impure metal. The rate and extent of corrosion increases with the amount of impurities present. Impurity of a metal generally causes heterogeneity and form minute electrochemical cells, and the anodic part gets corroded. Means as the impurity increases, the extent of corrosion also increases. So let us take an example of zinc. Suppose zinc metal contains some impurity such as lead or iron. Then what will happen? You know that zinc lies towards the anodic end and this other metal ions lies towards the cathodic end. Even if a little impurity of lead is present in zinc, a very small minute electrochemical cell will set up where zinc will act as an anode and it will undergo severe corrosion. Hence, purity of metal affects the rate of corrosion. The next is physical state of metal. The rate of corrosion is affected by the physical state of metal. The smaller the grain size of metal or alloy, the greater will be its corrosion. Moreover, area under stress, even in a pure metal, tends to be anodic and corrosion takes place at these areas. It's very, very important. Let us see these examples. Like you know that the portion of the metal which is at the grain boundaries is always under stress because the valencies are not satisfied. So you can see here the grain boundaries are the stressed part, and because they are stressed, they will act as a anode. The second example, if you take a metal plate and bend it, then the portion of the plate which is at this bent position is always under stress and it will act as an anode and will undergo corrosion. Hence, physical state of the metal also affects the rate of corrosion. Then solubility of the corrosion product. Now, if the corrosion product is soluble in corroding medium, then the corrosion proceeds at a faster rate. Otherwise, if it is insoluble, corrosion will be suppressed. So let us discuss an example. If lead is placed in H2SO4, a layer of PbSO4 is formed on its surface, and this layer is insoluble in the corroding medium. Hence, the corrosion proceeds at a smaller rate, as lead sulfate forms a protective layer around the lead. So solubility is very, very important point. The next is volatility of the corrosion product. If you know that when a metal is exposed to environment, for example, oxygen, a metal oxide is formed. But imagine that the metal oxide layer formed is volatile in nature. Then what will happen? It will soon evaporate and a fresh metal surface is again available for the attack. Hence, if the corrosion product is volatile, it evaporates as soon as it is formed, thereby leaving the underlying metal surface exposed for further attack. This causes rapid and continuous corrosion. The example, when molybdenum is exposed to oxygen atmosphere, molybdenum oxide is formed, MoO3. It is highly volatile. So it vaporizes soon and again a fresh surface is available for attack. Hence severe corrosion takes place. So these are all factors which are covered under the nature of the metal layer. Now let us see the nature of the environment. How does it affect corrosion? The points are presence of moisture, then temperature, then effect of pH, then presence of impurities in atmosphere, then presence of suspended particulates in atmosphere and conductance of corroding medium. Now presence of moisture. The greater is humidity, the greater is the rate and extent of corrosion. This is due to the fact that the moisture acts as a solvent for oxygen, H2S, SO2, etc. to furnish the electrolytes essential for setting up corrosion. So different impurities present in the atmosphere, they get dissolved in the moisture and they furnish the electrolytes. An increase in moisture increases the rate and extent of corrosion. Second is temperature. With increase of temperature, the corrosion rate also increases because the reaction as well as diffusion rate of ions in corrosion medium increases. Hence, temperature greatly affects the rate of corrosion. The next is effect of pH. Generally, acidic media is more corrosive than alkaline and neutral media. Hence, metals may be virtually classified according to pH range in which they will be affected or resistance. However, some metals like aluminum and lead, they are corroded in alkaline medium. So it varies from metal to metal. Then presence of impurities in atmosphere, very important. Corrosion of metal is more in areas near industry and sea. Why? Because near industry, you will have lot of particulates, lot of corrosive gases present in the atmosphere. And near the sea, the percentage of the sodium chloride is also present. So this is due to the fact that corrosive gases like H2S, SO2, CO2 and fumes of H2SO4 and HCl in the industrial area and NaCl of seawater leads to increased conductivity of liquid layer in contact with the metal surface. And because the conductivity increases, it also increases the rate of corrosion. The presence of suspended impurity is very important. Like some industries are there, like thermal industry, like power plants are there, then cement industry. These industry, they release lot of particulate matter in the atmosphere and they remain it in a suspended form in the atmosphere. Now, if the suspended particles are chemically active in nature, like sodium chloride, they absorb moisture and act as an electrolyte, thereby causing enhanced corrosion. And if the suspended particles are chemically inactive in nature, like charcoal, they absorb both sulfur gas and moisture and slowly enhance the corrosion rate. So these are also very important point. And the last point is conductance of corroding medium. Very, very important. Where the corrosion of the buried pipelines takes place, that time this conductance of corroding medium is very important. In non-acid soils, the conductivity, which depends on the moisture and electrolyte content, is a major factor governing the corrosive character. In such soils, corrosion follows differential aeration type of corrosion. This is a special type of corrosion which comes under the concentration cell corrosion, and here the corrosion takes place due to the difference in the concentration of air, that is due to the difference in the concentration of oxygen. This we'll discuss in detail in the next lecture. In highly acidic soils, the conductivity is not of much importance. In such soils, corrosion follows hydrogen evolution type corrosion. This hydrogen evolution type is one of the mechanism of electrochemical corrosion where the acidic environment is present. Hence, the rate of corrosion mainly depends on the pH of the soil and the presence of salt and oxygen. Hence, these are the various points which we have discussed under the factors affecting corrosion. Hence, the rate of corrosion depends on majorly, we'll just revise. The factors affecting corrosion are majorly divided into two parts, the nature of metal and the nature of environment. And this nature of metal and nature of environment is again divided into some subparts, some important factors that we have discussed here. Now, in my next video lecture, I'll be covering the mechanism of electrochemical corrosion and the differential aeration corrosion and the various forms of corrosion. So, thank you, students, for attending this video lecture. Thank you so much.